Hello, hello, it is me, Ugo, and this is the Practice Communicating Umpire. What problem is this specifically? I forgot the name of it. Check if number is sum of powers of 3. So, let's go through the steps, I guess. We're given an integer n, and we're supposed to return true if n can be represented as a sum of distinct powers of 3. So if we can have multiple powers of 3 added together, um, and equal to the number that we were provided in the input, then we're going to return true. Otherwise, we're going to return false. The important part is the distinct part, because if we didn't have the distinct part, then everything would be true as long as it's greater than 0, and that is true here because of the constraint. It's 1 to 10 to, I think it's 10 million. So everything would be true if that was the case, because 3 to the power of 0 is a number that we're allowed to use. And I'm assuming that the powers have to be integers. Yes, I'm assuming that that's what this is trying to say. So we can't have some fraction or decimal in the exponent, because then that would also probably give us infinite solutions. So yeah. That's the problem. The constraints right here, up to 10 million. And we know that we have to get this. We have to use distinct powers. We can't use the same one twice. So, my initial thought was, okay, we're going to find sums of powers of 3. So we just need to check every possible combination of them. Or at least that was my first thought. And because 3 to the power of something is an exponential, exponentials grow rapidly, I thought I could just quickly calculate it, and I mean I could. It is pretty quick. The maximum number of iterations that this can have is 15. I think maybe 16, like 15, 16, something like that. Before calling the sum exist function, which is a helper function I put inside of it. Oh, sorry. And so my initial approach is just backtracking. You know, you're going to check every possible combination after the current index. So we're not going to look backwards because we already checked backwards possibilities. And we're not going to check numbers that are greater than the current number that we have. So yeah, those are like the two things. Because if we have a number or power that is greater than the number that we were given, there's no point in checking that. There's nothing you can add to it that's positive, or a power of 3 that would get you back to n. So we can't overshoot it. The best we can do is equal to it. Otherwise, all the powers that we have available to us are going to be less than n. So after finding all the powers of 3 that are valid, we pass it into the sumExist function. SumExist is a recursive function that will take in the number that we have, that we're currently on. The powers of 3 lists, I could have probably just made this a self, or like a variable for an instance variable rather than having to pass it in, but it's fine. And we're passing in 0. 0 in this case is representing the index that we're currently on, so we're going to be iterating through the indices of the power of 3, and we're going to be checking to the right of it and looking at all possible combinations of sums that we can have from there. So that's why we have the index here, because we're just going to be incrementing it whenever we call the function to go forward. And yeah, I mean, let me see if I could, let me just pull this one out. Okay. So if we look at this is my my notes. So we're going to recursively check it the base cases are going to be n is equal to 0. So if n is equal to 0, we're going to have a match. And this is because we're going to be subtracting the current power that we're on based on the indice from the number that we have until we either get to n is less than 0, n is equal to 0, or we surpass the numbers in the list. I don't think that would be possible, but I just put that in case. But yeah, these are like the 3 base cases. This one probably never triggers, but I just didn't want to. I didn't want to risk it. So this one will just check. Okay, eventually we're just subtracting the powers. We're subtracting the powers repeatedly. So in the case of 91, we check 1, we subtract 1 from it, then we pass that into the function again. We have 90 this time. We try 90 minus 3, pass it again. 87, 87 minus 9, pass it again. We just keep doing that. So as you can see here, we check the base cases, then we assign current to be the element at the index that we're currently pointing to, which would be 0. So current is set to be equal to 1. 1 is not greater than 81. So that's our other check. If the current power that we're on is greater than the number that we have, then we have overshot it, and we're going to want to return false because that is not a valid path to take. But in this case, it doesn't fail, or that condition is not true, so we're not going to return false. We're actually going to continue, and that's when we get to the recursive functions right here. These two will cause a recursive call. In this case, we're going to subtract n. We're going to subtract current power, the current power from n, and then we're going to increment the index. So that's what we're going to do, and then we're going to move to the next call, and we're going to keep doing that until we either get to one of these cases. Eventually we'll get to one of the cases. We're going to return either false or true. If it returns true, then we're just going to return true, and that's going to take us all the way back to the start. If not, if it returns false, then we will move forward to this, because then the if statement is not true, so we don't return true. We return whatever the function, or we're going to do another recursive call with the current number that we still have. So we're going to stay with the same number, but we're going to increment the index because we haven't triggered the greater than condition, but we haven't found something that had, or the path with this power, there is no path that is successful with this power. So we're just going to go to the next power, and then we're going to check again if there is a match. There shouldn't be because we haven't changed the n, nor this one will trigger because again we didn't change the n. But then we're gonna go to, I guess this one might trigger. Like I said, I don't really know. I just made sure that that wouldn't be an issue. But then we go back up here. If the index is still valid, then all we're gonna do is we're going to find the power at that index, and then we're going to check if we overshot it. If we didn't, then we're going to send that new one into the recursive call. And I think a good example of this is 91. 91 has this behavior happen because we go from 1 to 3 to 9 to 27 to 81. And then once we get to 81, it's false, so we backtrack. 27 does not have any other options after 81. So because 27 doesn't have any other options after 81, there is no other options. That one's false. There's no other true options, so we return false again. So false is here. False is here. We return false. We keep returning false. We go to 9. Like imagine 9. 9 is still in this condition. So 9, what it's going to do is it's going to get the false from 27. The false is going to go right here. The if statement is not going to get triggered. So then we're going to actually end up calling the function here, where we're going to increment the index from 27 to 81 without actually using the power. So then we're going to skip 27 and go straight to 981. And that's what's happening here. We go to 81. 81 is still false because then we'll get 94, not 91. So then we backtrack. There's no other element, so we keep backtracking until there is another element. We go back to 3. 3 has 27 and 81 still. So we skip 90, or we skip 9. We go to 27. 27 goes to 81. We still fail because we're at 122 again. Then we do the same thing with 81. 3 and 81 get to 85, and then there's no more values to be checked. So in that case, what's going to happen is we return false still because we're still less than it. So there is no match. Or no, not this isn't the one that triggers. This is the one that triggers. See, yeah, this is we check all possibilities. Yeah. So that's the case where we have a smaller value, but we've checked every possibility. There's nothing left, so we return false in that case. So we return false. Every path that 3 can take is now false, so we return false back to 1. So 1 is going to go back here. It's going to say it's false if we try to do 3. So instead of 3, we're going to skip it, and we're going to call the next one, that's going to be 9. And then we go with 1, 9, gets us 10. We try 27 and then 81, that fails. But then we try just 81 after that while skipping 27. So we're going to go 1, 9, and then 81. So that's going to be 1, then it's going to end up being 10, and then that's going to give you 91. So that's how that works. It's a, I think this is called a state tree. State tree. I have the nicest handwriting, I know. With mouse. But yeah, that was my original solution. I know it's a bit crazy, but yeah. So I was kind of hurt when I found out that there was a much easier solution that was also better. Thankfully, at least it worked. It didn't give me a timeout error. It worked. It runs. The logic's still the same. So at least that. But Satya and I think Fu had a different solution. So I tried that one. And as you can see, it's much simpler. I was not happy when I realized that you could just do this. So yeah. The reason this works is because you're using the mathematical property of modulo, where basically if you have something that gets you a remainder of 2, there is no way of making that up. If you have a remainder of 1, that is possible to make up. So when n modulo 3 is equal to 0, that means it's perfectly divisible by it. So that means it could be a power of 3. And we just keep checking that repeatedly until n is not greater than 0. But the reason we can deal with 1 is because we have 3 to the power of 0. I'm pretty sure that's the reason why we can do that. So the only one we have to worry about is 2, because there's no way of making up a 2. So yeah. And we just keep dividing it by 3 repeatedly until we either get to there being a 2 or we get to 0. And once it gets to 0, if we make it without having anything that's inside of it give us a remainder of 2 when divided by 3, then we return true. This solution much quicker, does not require the whole combination stuff that I was doing. It does not use recursion. It's nice, simple, while loop. I don't know why it's so bad in memory though, because like this is literally recursion. And it has a list that's being created as I go. Not sure why this one's worse in space time or space complexity, but I think it's just an LeetCode thing. But yeah, this is me trying to use backtracking because it felt like a backtracking problem, and then realizing halfway through, well, not halfway through, I realized afterwards that it was not worth the time. But I'm happy it worked at least. Yay.